Smartphones and electric vehicles share a common operational constraint. The battery should remain between 30 and 90% charge. Piercing through the metallic casing and finally into the chemical lattice reveals the physical reality governing that rule. The 30% threshold represents a hard physical boundary within the cell. Capacity fade, the gradual loss of a battery's ability to hold a charge, is a thermodynamic limitation. To understand it, we must deconstruct the electrochemical engine at the atomic level. This chart shows the electrochemical potentials of various metals. Lithium sits at the extreme edge of the scale, with an electrical potential of roughly 3.04 volts. Lithium possesses an atomic number of 3, with a single valence electron, a lone electron in its outermost shell, orbiting the nucleus. This single valence electron makes the atom highly volatile. To reach a stable state, lithium must shed this electron. This process of losing an electron is called oxidation. Once it sheds its negative charge, the atom becomes a stable, positively charged lithium-ion. The chemical pressure to reach this stable state generates the potential energy that batteries harness. Modern portable energy scales from the ability to trap and control this specific atomic instability. The central engineering challenge is providing a housing that stores volatile lithium safely while allowing its oxidation to be performed as work. A graphite lattice structure provides this housing. It acts as a rigid, layered matrix to hold neutral lithium atoms when the battery is fully charged. This graphite structure is the anode. It provides physical storage, but does not chemically react with the lithium atoms. Drawing energy from the lithium requires an opposing force on the other side of the cell, the cathode. In these cells, the cathode is cobalt oxide. When cobalt bonds with oxygen, it achieves a +4 charge state, becoming highly electronegative. This causes the cobalt oxide to aggressively pull in free electrons. This process, gaining an electron, is called reduction. This creates a constant chemical tension. Lithium seeks to lose an electron, while cobalt oxide seeks to gain one. The stark difference in electrochemical potential between the unstable metal and the electronegative compound drives the entire cell. If the lithium and cobalt oxide interact directly, they will transfer electrons in a rapid, useless release of heat. To prevent this, a liquid electrolyte layer is placed between the anode and cathode to dictate how particles move. The electrolyte serves as a perfect insulator against electrons. It is an impenetrable barrier to negative charges. While it blocks electrons, the electrolyte allows the free transport of positively charged lithium ions. When the lithium atom splits, its two components are forced onto separate physical pathways to reach the cathode. This selective permeability, blocking electrons while passing ions, enables the functionality of the battery. By enforcing these separate pathways, the electrolyte converts a chaotic chemical reaction into controlled electrical work. The discharge phase begins when an external wire connects the anode to the cathode. The pull of the cobalt oxide causes the lithium atom to split. Blocked by the electrolyte, the electron is forced through the external wire. This movement of electrons through the external circuit is electricity. This flow powers the motor or the processor. At the same time, the positive lithium ion travels through the electrolyte barrier to reunite with the electron at the cathode. Once the inventory of lithium has migrated to the cobalt oxide, the potential is equalized and the battery is dead. Restoring this system requires plugging the device into an external power source to begin the charging phase. External voltage overpowers the cobalt oxide. It strips electrons from the cathode and drives them backward through the wire to the anode. The positive lithium ions are repelled by the cathode and move through the electrolyte back to the graphite matrix. When the lithium returns to the graphite, the high potential state is restored. The daily cycle of charging and discharging consists of a controlled, reversible shuttling of a finite inventory of lithium ions back and forth. If this shuttling is reversible, dropping the charge below 30% should be harmless, yet it causes permanent damage. During deep discharge, the cobalt oxide cathode becomes tightly packed with lithium ions. When the concentration of ions is too high, they can no longer cleanly slot into the cobalt oxide structure. These excess ions undergo a secondary reaction, permanently bonding with oxygen to form inert lithium oxide. Lithium oxide is a stable compound that will not release its lithium ions, even when a charging voltage is applied. Capacity fade is the term for this permanent reduction in the active inventory of movable lithium. Exceeding the 30% limit triggers an irreversible stoichiometric loss of active fuel. Maintaining a 100% charge also degrades the cell through parasitic reactions, where lithium reacts directly with the electrolyte solution. While chemical degradation reduces the runtime of the battery, mechanical failure leads to the destruction of the device. The final component is the separator, a synthetic polymer barrier that prevents the anode and cathode from making physical contact. If this separator fails, the high-potential anode and cathode mix directly, bypassing the external circuit. This results in thermal runaway, an uncontrollable, self-sustaining chemical fire that causes the battery to explode. A lithium-ion battery functions as a high-precision chemical engine, where the state of charge acts as the primary defense against atomic loss and catastrophic failure.